continuing in 11.1, and the subject is negative feedback is required, and it often is required for op-amps. Negative feedback is the return of a portion of the output signal to the input signal and out of phase. When an op-amp has feedback, its operation is closed loop with no feedback. It is open loop. Okay, a couple concepts here to consider. Here we have two op-amps that are configured to use negative feedback. One is using the inverting input, and the other is using the non-inverting input. And it's needful to look at the differences in the configuration. Let's just look at, for example, here we have an input signal. Signal comes in like so, and notice it's inverting, so that signal will be just the opposite of that on the output. Now notice the signal comes in and a portion of it is returned to the input, and so here we have this signal coming in, and the returning signal is the same signal except that it is out of phase. Now this will tend to attenuate the final output. Now if we mentioned something about closed loop and open loop, and often you'll see a term called AOL, not for America Online, that is for gain open loop. And gain open loop is not real stable. It's kind of like beta was in transistor. And the open loop gain, for example, for a 741 can be anywhere from 20,000 to 100,000. Now, gain, and we call this gain ACL, this is for gain closed loop, and that's what we're looking at when we incorporate negative feedback, is gain in a closed loop configuration. So if this resistance wasn't here, you'd feed the input and it'd come out here, and there's no loop at all. It's just open loop. Now when we close this loop like this, that's why we're calling it gain closed loop. And when we do this, we can get a very predictable gain. Now, the diagrams here, let's see, we're using inverting and non-inverting. Okay, we looked at let's look at the non-inverting. Now, in the non-inverting, we're going to send in this input signal, and since it's the non-inverting, the output will be the same phase as the input. And then we have a portion that is fed back to the inverting input, and so notice that is coming in like this. It's in the same phase. Now recall that an op-amp amplifies the difference. Now if we have the same phase of input on both inputs, then again this will tend to attenuate the signal. And so this idea of negative feedback is that the feedback opposes the original input signal. Now again, this will attenuate the total gain from what we would have in AOL, but again, it will make for an ACL, which is a closed loop gain, and it will be an extremely predictable amount of gain. Since the op-amp ideally has infinite input resistance, no current flows into the input. Now remember, we've mentioned that several times, that this effectively has infinite input impedance. So what we're going to say is that we're going to send in an input voltage, and it will go across this resistance. Now there's something that we haven't mentioned. There is a concept, sometimes it's referred to as a virtual ground, sometimes a virtual short. In this case it would be referred to as a virtual ground, and we can consider that there is a at least for calculation of current, we can consider that there is actually a ground between here and now. If it was a real ground, there we would have no output, because simply the signal would come in and go straight to ground. It would never get to the amp. But this is a virtual ground, but because for calculation purposes and analyzation, it does look like a ground. And so if we took this this voltage in and we divided it by the resistance here, we would get a current, and that current is not going to flow into the op-amp because it has infinite resistance. That current will be felt through this resistance up here. Sometimes this is referred to as RF for feedback resistor, and that the value that flows through that current will develop a voltage, and that will result in our output. And so what we're going to find, and we'll look at negative feedback in more detail later, but what we're going to find is that we can get a very predictable gain based upon the sizes of these two components. And the same concept will result down here. We call this a virtual ground. Oftentimes in this case, it would be called a virtual short, because if you calculate the value of this voltage across this component, then we can do basically the same kind of calculation. Okay, output resistance. The output of an op-amp comes from a source internal to it that has an associated series resistance. And so here we see the input, and we see an associated series resistance that's going to become our output resistance. The effective resistance is called the output resistance of an op-amp, and we looked at that when we were back in the transistor section. Negative feedback lowers the effective output resistance. It is low enough that for practical purposes we will consider it to be 0. Now, with the 741, just as an example, it has 25 ohms of resistance with gain open loop, and nearly 0 with negative feedback. In fact, if we went in and did the formalized calculations for that, we would find that with negative feedback, the resistance is usually less than 1 ohm, and so for practical purposes we consider it to be 0. Output voltage swing. The output of an op-amp can normally have output voltage swings that are within 2 to 3 volts of the supply voltage. If the output tries to exceed these limits, it will be distorted. It will result in clipping. We will have saturation in one of the output transistors, and where clipping occurs, it is commonly referred to as the rails, and we'll get to that in a couple minutes. Okay, so here we have some examples, and here we have an amplifier with, in each case here, the gain is 1 million. The supply voltages are positive 15 and negative 15. The only thing that is changing is the input and the output. And so in this case, here we have 1 microvolt of input, and so we come in with 1 microvolt, we amplify it 1,000,000 times, and it has 1 volt of output. And so the input and the output have the same shape, except that it's been significantly amplified. Then in the next screen, or the next circuit here, everything's the same, except now we're putting in 10 microvolts, and so now we're getting 10 volts out. Next screen, we feed in 15 microvolts, and now the op-amp is unable to provide that much amplification. We're sending in a signal, but the supply voltages are going to limit our output. Now notice that we're not getting all the way to 15. In this case, we're getting to 12, and this value will actually vary depending upon what the size of the load resistance to the side. If you have a very large load resistance, you might get a little more than that. If you have a very small load resistance, you actually might get a little less than this. And in this case here we have 20 microvolts, and again now we're having severe attenuation, and the output signal is going to look kind of like this. It's almost beginning to look like a square wave, no, not quite, but it's getting there. And these signals where it is clipped off, this would be referred to as the rails of the op-amp outputs, because it's the limitation where it can't go any further. Okay, open versus closed loop gain. We've alluded to this already. An ideal op-amp has infinite voltage gain at all frequencies. Well, this isn't going to be true, but we'll just say that's ideal. Practical op-amps have open loop gains ranging from 100,000 to over 1,000,000, and notice this, at low frequencies. We will look at a graph in a later presentation. the internal voltage gain of an op-amp decreases at higher frequencies. And so when we look at this graph, we will see this decrease in frequencies as, the decrease in voltage gain as frequency increases. Okay, we've looked briefly at open and versus closed loop gain. We looked at output voltage swings, output resistance, and we talked about the concept of negative feedback, which is usually used in operational amplifiers.